Ready?
Yeah.
Okay. Well, welcome everyone. It's a lecture note on our fourth summer school on quantum computing. We have a very special guest this afternoon, Professor Camille Coti. She's an associate professor at the ETS, which is the École de Technologie Supérieure of Montreal, which is a school of the University of Quebec. And she obtained a PhD from Université Paris Sud in 2009 and is interested in high-performance computing systems, including quantum processing units. I believe we met Camille, I think last year, Camille? No? But this mean because of a happy happening, which is that the ETS has currently quantum computing. It's 24 superconducting qubits. And I understand it is the first quantum computer in Canada whose primary purpose is to serve researchers at public academic institutions. Maybe you can later tell us a bit uh, this this computer, Camille. But for the time being, well, we are ready for listening to your conference. Thank you very much for agreeing to lecture this lecture. So whenever you want, you can start your conference. Thank you.
Well, thank you very much, Boris. And thank you very much to Boris and Jimena for inviting me today and to Victor for organizing it today. Like I was telling Boris and Jimena and Victor earlier, I've never had the chance to actually go to Mexico. But I've worked with people from Mexico and they were amazing. And, it seems like your universities are thrilling and offering amazing programs like the summer school on quantum computing. So I'm really happy to talk to you today. So I'm going to share my screen. And actually, I've prepared some slide, but it's going to be very progressive. So I'm going to draw a lot on the slides, etc. Because I come from the world of high performance computing, as Boris just said, and my interest is how can we use a quantum computer in a high performance computing context. So I want to introduce the quantum processing unit as an accelerator for certain types of computations. So I'm going to explain the challenges for that and the leads that we currently have towards that. One specificity of the 24-qubit quantum computer that we have in Quebec is that it's sitting in the same room as our supercomputers. So it's on premises. So I'm going to explain why it's so important and why it's so specific. So when we talk about parallel and distributed applications, we have distributed resources. So usually when you run a program, you're running it on a single computer. But when you want to run it on distributed resources, you have multiple computers. You have all these computers, and each of these computers has their own operating system, has their own memory space, has their own application scheduler. And so they're independent entities, and you want to group them all together into a single computer, a single machine, a distributed machine that you're going to program in a specific way, but you want them to run and to work together. And usually for example, when you're sitting in a lab room, you have a bunch of machines in front of you, but they are separate machines. And the challenge is to make them work on a single application all together. So how do we do that? So usually when you run a program, you're running it on a computer. So you have these two computers that are running a program each, and you put them all together, and each of these computational resources, so each of these computers are running a program, but they're running it independently. So for example, if I'm going to draw. So I got a tablet to draw things and on the slides to make things more interactive. So if my tablet, yeah. So for example, you're running a program on this machine, and there's absolutely no reason for this machine to have access to what's happening on this program. So for example, if I'm running something, okay, I'm running a program and I'm writing Boris here. Sorry, Boris, you're going to be my victim today. So I'm writing Boris here. How does this computer know that I wrote Boris here? Okay, they're connected by the network, but each of them has their own memory space. And well, for obvious security reasons, I cannot read in the memory of another computer. I cannot read in the memory of my neighbor's computer. I cannot even read in the memory of a computer that's sitting in the same room as mine. So we need to be able to run a program on all the resources at the same time. So for that, we have a component called a distributed runtime environment. So it's distributed, of course, because it's running on a set of distributed resources. And what does it do? So it runs an application on multiple distributed resources. It allows you to use all these machines all together. So it starts the processes, it monitors them. So for example, it sees, okay, there is a failure. So what are we supposed to do when a process fails on a machine? And it forwards signals on I/O. So for example, if one process on the machine does printf and prints something on the terminal, you want to be able to see it. Or if you send a signal, you want all your processes to get this signal. But the problem is that all your processes are on nodes, on independent nodes and independent machines. So you're going to need this distributed runtime environment, this distributed application to do all of that. And also it supports the parallel programming model. So you're going to program your application to be able to use all these distributed resources, but you're not going to program that the way you program a single computer. So maybe some of you are familiar with parallel computing using threads or C++ promises and futures, that kind of things. And we even have different programming models because we have disaggregated memory. So we don't have a single memory that everybody has access to. Each process has its own memory. So we need to be able to program applications that are using all of that. So for example, I mentioned earlier that, for example, you can have a machine that has, so you have a machine here that has Boris written here. And you have a machine here, and you have a process running on this machine, and this process wants to know, okay, what's written here? So you have no choice but using the network. So you're going to do a network communication and say, okay, what did you write here? Okay, I wrote Boris, and then you get the data here. So we have parallel programming models to program this type of systems. But they cannot communicate just by chance, and they have we need to support the programming model, so to enable communications, whatever communications are being used by the programming models. But the programming model needs to be supported by their distributed runtime environment. So for example, if we have, let's say that we're using TCP/IP and we have one process, okay, that opens a socket. Okay, what's the IP address of the socket? What's the TCP port or the UDP port that's being used? Or if this machine has a specific network card for high performance computing, for example, an InfiniBand card. So the programming model needs to know the parallel programming environment needs to know, okay, I can reach this process using InfiniBand and using this contact information. So all of this is being handled by the distributed runtime environment, so that all the processes running on different computation nodes are able to work together and to be part of a single application, although they're running on very independent sets, on a set of independent resources. So now, practically speaking, how does it happen? So first, I made a little picture. So first, the user starts the application from a specific node that we call the front end. So the front end is the point of contact between the user and the application. So you don't, when you're running a distributed application, you're not connecting on each and every computation resource that you have. You're connecting on a single a single machine called the front end. And the front end will give you access to your application, will start running the application, and it will be the point of contact between your distributed application and yourself. So you have the front end and you have the computation resources. So you start the application from the front end. So you start the application and the runtime environment deploys a set of daemons. So there's going to be a daemon on each of the computation resources. So that's the local presence of the runtime environment of this distributed middleware that's supporting everything. So you have a daemon that's executed on each computation resources, and they interconnect together. So they connect to each other and such in a way that they form an overlay network. So it's a communication infrastructure. It's connected. So the front end has a link, has a network path to each and every of these daemons. So to each and every of these computation resources. So now we have a communication infrastructure, and the communication infrastructure is used to send commands. So these commands can be to start the application first. So the first command is, okay, start this application on the computation node. But then it can be also, okay, for example, this process printed something. So it did printf blah. Okay, so it did printf blah. So my print is going to be sent over the network all the way to the front end. And so the user in their terminal is going to see blah. Okay, so this communication infrastructure is being used to communicate and to perform all the commands that are supporting the application. The next step is to, well, now in green, what I wrote in green, my little green rectangles are representing the application. The next step is that the application will want to communicate, will want to, for example, if I want, let's say, if I want to send a communication between this process and this process here, so I want a communication there, okay? So this process will be the sender, and this one will be the receiver. So how does send know how to contact receive? So each process has some contact information. So I write it, it's CI, so contact information, CI. And so send is asking its local daemon, how do I contact receive? What's receive's contact information? And there is actually an operation that's happening between all the daemons there. So all the daemons are collecting the contact information of their daemons, of their processes, sorry, and they're exchanging them so that when send wants to send something to receive, it asks its local daemon, and the local daemon says, oh, here is their contact information. And now send can connect and send something here. That's necessary for portability purposes. We cannot say, okay, let's just have the IP addresses hard-coded into the program, and let's agree on a port that we're all going to use. So first, if you're using IP addresses, well, if tomorrow you're running on a different machine, it won't have the same IP addresses. And you cannot agree on a port and say, okay, we're going to use port 50,000. Because if tomorrow port 50,000 is used by something else, what do you do? So for example, if tomorrow on this particular node, so let's use a different color, let's say here, you say, okay, I want to use port 550K. I want to use port 50K. I want to use port 50K. Oh, no, too bad. On this specific node, somebody else is using port 50K. Okay, I'm going to use port 50K plus 1. And then if this process tries to connect on port 50K and it's already busy, it's already taken by something else. For example, I might connect to something that's not actually the process I want to connect to or something like that. So, okay, I need a mechanism to know that processes are not using the port I'm I'm expecting them to use. But it's the same problem. How do we tell other processes which port we're using? So in that case, we say, okay, we don't make any assumption on the port that people are using, and we cannot even make any assumption on the type of network that processes are using. That because on high performance computing machines, okay, we have Ethernet cards, but they're mostly used for the runtime environment, for the communication infrastructure. So for this infrastructure that I wrote in the middle here, the application communication, so the communication that I wrote in orange there, that I drew in orange there, are generally not using an Ethernet network. They're using a high-speed network. And when you're talking high-speed network, okay, you have InfiniBand, but you also have Quadrix, you have MyRenet, and you have different kinds of networks that are high-speed networks that have a very low latency, a very wide bandwidth. They're super high performance, but you cannot tell before somebody tells you what technology, what kind of network the remote process is using. So we need a step where processes discover how they can be contacted. So they discover the contact information and they share it through their daemons of the local of the runtime environment. So they are sharing it with they're telling their local daemon, okay, I can be contacted with that. And then the runtime environment share it together so that every process knows how it can contact the other processes. Today we want to talk about how we integrate quantum processing units in high performance computing. So that's typically heterogeneous computing because we want to have a high performance computer together with a quantum processing unit. So that's heterogeneity. But heterogeneity is not something new in the, excuse me. Sorry. Heterogeneity is not something completely new in the world of HPC. So for example, in the application, we can have heterogeneous data sets. So for example, you have a data set, you have a lot of data that you want to process, but every piece of data is taking a different time. So for example, you can have, let's say, points that you want to process, and some points are going to take a couple of microseconds, and some points are going to take minutes to process. So when heterogeneity is in the application, we know how to do that because we can use load balancing. So we have load balancing mechanisms and scheduling algorithms, scheduling heuristics. We have self-adaptive algorithms, etc. But it must be permitted by the programming framework. So the framework needs to be able to let you balance the load and schedule your computations across your resources. And it's also applicable for when you have computers that have different speeds. So for example, you have a bunch of computers that you've put together to build your own supercomputer, but you have very new and very powerful computers, and you have older computers that you've put together. So you have computers that process at different speeds. And of course, the consequence is going to be that your application will be processed faster on the newer computers and slower on the older computers. But that's okay. You're going to have to handle that in your application and to balance the load well, and you can do that. Now, when we talk about hardware, heterogeneous hardware, that's a different story. For example, is your hardware binary compatible? So one thing we can do in high performance computing is to start a different binary on the different nodes depending on the application, depending on the hardware that you have. So for example, if you have, let's say if you have RISC computers and CISC computers, you're going to start a different binary. Then there's a problem of number representation, of data representation. So for example, if you have big endians and little endians, then you have to handle conversion somewhere in your communications between your nodes. So that's also something that the runtime environment helps handle. It's part of the information that's being shared by the runtime environment. But then when we're using GPUs and FPGAs in distributed applications, well, even in parallel applications. For example, if you're running a CUDA code on your computer, GPUs are not binary compatible with CPUs. So you have your code that's running on your computer, and then you call a function that's being executed on the GPU. And well, the problem is that it's not binary compatible, so it cannot be just like calling any function. So something that you can do is to start another binary, or something that's being done for GPUs that actually in the binary that you're executing on your computer, we call that a fat binary because there's the binary for your CPU, and embedded in the program there's the binary for the GPU. So first, it's not the binary, it's the bytecode, and it's compiled just in time the first time you're calling the function, but it's actually embedding both binaries. So you have your program that's running on your computer, and it's starting a function which is actually in a different binary format. So that's the way we're handling heterogeneity, binary heterogeneity in parallel programs. But now when we talk about quantum computers, that's completely different. Because, well, first, the hardware is not binary compatible, but even the programming model is very different. So for example, on the left, well, in the middle, I put some code that I wrote for lab. So that's just a function that's doing some matrix operation. And here, so for example, I've put okay, that's very random. So I've drawn that for just for this, and it's not a real program. It's purely random. I drew a few gates, but you know we have these programming models where we write lines and we give instructions, and we have these programming models. So and now I'm talking about gate-based quantum computing, but we have different models. We have other models. So how do we put that together? And how can we make a hybrid program using two architectures that don't even have the same programming model? So currently, quantum classical hybrid programming is very, I wouldn't call it mainstream because quantum computing is not mainstream, but people who do quantum computing are often familiar with that kind of programming, of hybrid programming. Because, for example, very popular algorithms in quantum computing are iterative algorithms such as QAOA or Falcon, where you have it's exactly what I draw here. So you have a classical part and you get the result of the classical part. So for example, the classical part is picking a number. And then you have the quantum part that takes this number as an input parameter, and it's producing something. So for example, it's producing let's say a result, an optimization result. And you take this result as the input of the next classical part that's producing something else, another result that's the input of the quantum part. So it's very sequential. You have, you run the classical part, you get a result. The result is the input of the quantum part. You get a result that's the input of the classical part, etc., and you loop. So how do we do that in practice? Well, in practice, we have two different programs, and each program takes something as an input and produces something as an output. And the output of the classical program is the input of the quantum program, and the output of the quantum program is the input of the classical program. So we have two different programs. We have two separate programs that take inputs and produce outputs. We have two separate runtime environments. So we run something on the HPC part, the classical part, we get an output, then we submit something to the quantum computer. We wait in queues because most quantum computers are in the cloud. You guys are lucky at UNAM that you actually have the machines in front of you. But often you have to submit it to a queue because it's in the cloud, and you get once your circuit goes through the queue, you get a result. And then you submit that to the queue of your local HPC platform, and you get the result, etc. So it's very asynchronous because at each step you have to wait in queues. Now, the next step would be to have something more integrated and more synchronous. So the idea is that, well, you've probably seen that quantum computers are good for certain types of computations. They're going to be super fast and unbeatable by classical computers on specific types of computations. But they're not good for everything, and you cannot even compute everything on that. So we want to use the quantum computer as an accelerator, and it's going to speed up some parts of the computation. It's going to be used on what it's good at. So we're going to run the program, and we're going to offload some parts of the program on the quantum computer. And we're going to proceed with the rest of the computation on the classical machine. So we want to have something more synchronous. And for example, I drew a DAG on the bottom part of the slide where we have, so for example, we have the classical part, and the classical part is producing something, an output. Part of this output is used for another classical task, and part of this output is also used on the quantum part. The quantum part is doing its life, and we're we're going to have a scheduler that's going to say, okay, this is supposed to run on the quantum machine, so I'm going to run it on the quantum machine. And this is supposed to run on the classical machine, so I'm going to run it on the classical machine. And then the classical part is living its classical life on the classical computer. And in the meantime, what's supposed to be running on the quantum part is running on the quantum part. So that raises a lot of challenges, and a lot of very exciting challenges, because how are we going to run that in practice? So there are some challenges. So we need a runtime environment that's able to run on both machines, on both the classical machine and the hybrid machine. So what I mentioned is that most machines are in the cloud nowadays. So you submit something to the cloud and you get the result after, your circuit is going through the queues, and then it's being scheduled. It's time to run, and you get the result. That's something particular that we have in Quebec is that the quantum machine is located in our machine room. It's actually in the basement of my university. And so we have the supercomputers, and we have the quantum machine. So we can actually put the network link between the two machines, and we can have a distributed program that's running on the two machines. Also, we need a runtime environment that's running over both machines at the same time. And we need something that's binary compatible, meaning that from either machine, we need to be able to run something on the other machine. So we need to be able to have a program that can call functions on the other machine. And that's a very specific challenge, because well, I'm not even talking about the binary incompatibility like with CPUs and GPUs. Here we don't even have the same programming model. So we need to find a way to run applications on both machines, and they can both work. Also, we need to enable communications between both machines. So we need to be able to start a computation on the remote machine. So for example, on my DAG here, we can need the classical part here to be able to start a computation here. I'm going to draw something thicker. How do we do that? So we need to at the end of the classical part, we need to be able to trigger something that's going to run on the quantum machine, and vice versa. Once the quantum machine is done here, it needs to be able to trigger a computation on the classical machine. Okay, so we need to be able to communicate first to start a computation, and also to get the result, because the result here is produced on the quantum machine, and the classical part needs it. So it needs to be communicated between the two machines. Okay, so they need to communicate both to send and receive data, but also to start computation on the other machine. And last, we need to schedule computation on both machines, because, well, my little DAG is really cute, but okay, how do you know that once there's a synchronization, I'm going to draw it like this. Here we have a synchronization, because this task cannot start before both of these tasks are done. So we have a synchronization. For example, what can happen is that this task is usually we draw that using Gantt charts. So you have a task there that runs like this. So it can be this task here. And you have a quantum task that's running. And if the quantum task is taking much longer, like this, okay, what's going to happen is that when I have this synchronization here, there, so I have this synchronization here, and I have a classical task that starts right after that. So what you can see is that here, the classical machine is idle. It's waiting for the other task to finish. And so you really don't want that. Or it can be the other way around. You can have the classical task that finishes, that takes really long time, okay? And you have the quantum task that's super fast because quantum computers are super powerful. And then, well, it's the same here. Your classical task that's coming after needs to wait for both tasks to be done. So you're here. And so you have this task here, and after this task here is starting two quantum tasks. So how are you going to do that? Are you able to, okay, here you have a synchronization. Are you able to start both tasks like this in parallel? So is your quantum computer able to run both tasks in parallel? Or are you going to have to linearize them? And I'm going to write them linearly like this. Are you going to have to linearize them? But in both cases, in both situations, the quantum machine is idle there and there. So this problem that I'm mentioning, and to avoid and to minimize the idle time, so the black lines that I wrote, it's a scheduling problem, and it's a really non-trivial problem, because because we need, so first, scheduling is it's a combinatorial problem, so it's a combinatorial optimization problem. But also, you might not know how long your tasks are going to take. First, because, well, I had a professor who used to say the crystal globe machine has not been invented yet. So computers cannot predict the future. So when they start a computation, they don't know how much longer it's going to take. So you have to make heuristics. Sometimes you have a model on how much time your task is going to take. Sometimes you have to take a guess and to have to make heuristics. So scheduling over heterogeneous resources is super hard. There's some ongoing work, and the research community is working hard to do that for GPUs. But quantum computers, it's a different animal, because they're running at a very different speed, but you also have a latency to prepare the qubits and to start the computation. You also have a latency because you're going to have to convert your data between classical and quantum, and between quantum and classical. So even just once we're going to have a runtime environment for that, we're just executing applications efficiently is going to be a big piece of work as well. So here are the challenges that we're having currently to take advantage of all the power of quantum computing for well, hybrid classical and quantum computing. So I would like to thank you very much for attending my talk. And if you have questions, I would be delighted to answer them. And yeah, since I have this beautiful tablet, I can even make drawings to explain things, etc.
Oh, that's great. Camille, thank you very much for such an interesting and relevant talk. We are sure that this talk will encourage many of our enthusiastic participants. So we have several questions from our audience that we'd love to ask you. So here we go, if you agree. Okay, first one. What does start another binary mean?
So when you are executing a program, For example, you're clicking somewhere or you're typing a command, it's actually running, so the program is actually a binary file that only your computer can understand. You might be able to understand, but you might have to work a little bit to uncipher it. So the program that's actually running is in a binary format. The problem is that how do we go from something readable by the human to a binary? And what's the convention for this binary format? Well, I'm sorry, but there's no convention. There's multiple conventions. So for example, you have for example, you have the Intel ones. Well, there's multiple versions, but the current one, you have one that's pretty much all the Intel processors understand. You have some very specific optimizations that can be specific to some generations of CPUs, but that's very specific. But when you don't enable any such optimizations, okay, all the AMD and Intel processors will understand that. PowerPC, for example, which is very popular for high performance computing, it's a totally different story. You cannot run Intel binaries on a PowerPC computer. And ARM is another different story. So for example, if you have a MacBook, one of the recent MacBooks, you won't be able to run programs that were compiled, so prepared, binary prepared for Intel machines. So the problem is that when you have an architecture, you have a binary format, but the binary formats are very specific to architectures. And unfortunately, GPUs don't have the same binary format, and quantum computers don't have the same binary format just because it's not even the same execution model. And I talked about gate-based quantum computers, but it can even be different.
Thank you very much. Next one. How can we efficiently manage shared quantum resources in a multi-user environment?
Oh, that's an excellent question. And I don't know if you, Victor, if you're seeing Guillermo's question in the box. I'm probably going to answer that after. So do you mean classical resources or quantum resources? Because for classical resources, we have something we call a batch scheduler. So basically, it's a database. It's a database that's keeping track of all your nodes, all the nodes of your computer, and it's saying, okay, I reserve this node for Victor and this node for Boris and these two nodes for Jimena. And nobody else can use them because the batch scheduler is also in charge with starting your program and these resources. And for example, let's say that Boris is done with his computation. Okay, Victor is asking for another node. Okay, let's assign this node to Victor. That's easy because on a supercomputer you have a lot of machines, but if you're using a computer, you're not disturbing the computer that's sitting next to it. Well, you can disturb it a little bit if you're overheating, and there are some effects of some neighbor effects that are caused by heating and that kind of things. For quantum computers, it's a different story. First, because on most quantum chips, when you're measuring the state of your qubits, you're measuring all the qubits. And when you're measuring, you're collapsing the state. So when you're measuring, let's say that you want to measure 2 qubits, the other qubits are going to be collapsed. So you cannot say, okay, I'm going to give these 2 qubits to this application and these other qubits to another application, because the first one that's going to stop will want to be measured and it's going to collapse the other application. That's the first problem. The other problem is that you have crosstalk between your qubits. And if you're sharing the quantum machine between 2 users, well, they're going to, their circuits are going to disturb each other. But something that we've noticed is that you only need to put 1 qubit of separation to avoid this problem. So I'm going to draw something. Let me close something, and I'm going to draw here. So let's say that, where did I put my pen? Okay, it's here. So let's say that you have qubits like this, and you have, okay, and you have a circuit. You have a pink circuit. You have a circuit that's doing things like this. Okay, and you have a purple circuit that's doing things like this. Okay, yeah, my gates are not very beautiful, but okay. If you're doing it like this, and so let's say that your qubits are interconnected like this. Okay, so that's actually that's the topology we have on Monarch. Yeah, like this. The topology we have on Monarch is like this. So let's say that you have you have your purple circuit that's running there, and you have your pink circuit that's running there. So the problem is that you have a physical connection between these two circuits, and you're going to have crosstalk there, and it's going to lower the fidelity that you have between your two circuits. So you're going to have so it's going to lower the fidelity of these qubits. So you're going to have additional noise that's being caused by the other application. But something that we noticed is that if you have your circuit like this, so I'm going to draw it again. So you have your quantum chip like this. Okay, up, 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 up. So I'm going to put the pink circuit like this. Okay, and I'm going to put 1 qubit of separation. So I'm going to sacrifice this qubit and sacrifice this qubit. And then I'm going to have my purple circuit. So for example, using this. And now there's no crosstalk anymore. So we have, we have this separation, this strict separation, and there's no, well, it just as if there's no connectivity. We've lost connectivity between our two circuits. We've disconnected our two circuits, and now there's no crosstalk anymore, and we don't have noise anymore. So we can do it like this. The other problem is now, let's say that which color am I using? I'm using this. Let's say that you want to measure the state here. Okay. The problem is that you're going to need to measure all your qubits at the same time. So what you're going to want to do is I'm going to draw a Gantt chart. So you want to schedule your circuits such in a way that they end at the same time, like this. Why end at the same time? Because let's say that you have your two circuits like this, and one ends later than the other one. Okay, so here these qubits are idle here, but things are happening on the machine, and well, idle qubits are very sensitive, and they can produce some noise from inside of the machine, etc. So it's going to cause some disturbance, and you're going to have a lot more noise that when you're measuring your upper circuit, when you're measuring it here, you're going to have a lot more noise than if you had measured it here. So you want to do it the other way around. So you want to first schedule the longest one, and then schedule the shorter one here, so that you measure them at the same time. And it's okay if they're either here. You can do things. So for example, you can turn them here and there, and you can make them dance so that they are not disturbed, and they're not being idle and causing some noise to themselves. So so yeah, we have this. Another solution that we have is that IBM machines allow mid-circuit measurement, and mid-circuit measurement is just something that we all dream about. So let's say that you have a bunch of qubits like this, and you can decide to measure only these ones, and the other ones can continue with their life. So yeah. So that was a very interesting question, and that's some ongoing work that we have here.
Yeah, and your explanation was very illustrative.
Thank you very much.
Yeah, I'm gonna keep reading questions to you because we are receiving them in the Discord server of the Quantum Computing School.
Okay.
That is why you cannot see them on.
But there's a question in the
Oh
box.
yeah, I can see there is one.
Yeah.
Well, if you want to go for it, it is okay because that was the next one.
Okay, so Guillermo Cabrera, did you identify limits of processing running in a controlled way on this hybrid situation? So the very first limit is that we need to be able to express the application using this programming model. So it's just one program. So the very big question we have in high performance computing is to provide programming models, parallel programming models that application people can express their computation into. So the very traditional way is to give MPI program. So with MPI, you run a bunch of processes and they communicate together with two-sided communication. Sorry, you send, you receive. The thing is that you have so first it's difficult. It's not trivial. And you can ask my students who just finished a 4-month class on parallel programming, and they probably thought that was the hardest model that they saw during the term. And the other problem is that not all computations can be expressed in terms of send and receives. So we have other programming models so that, people who write parallel programs are not computer scientists. They are chemists, they are biologists, they are physicists, and what they're interested in is their computation. But so we want them, we don't want them to have to bend their algorithms and their computation patterns so that they can fit into in the programming models that we're providing. We need to provide them with programming models that they can express their computation in. So one major limit of what I just presented is that you need to be able to express your application in terms of tasks in terms of tasks that can take inputs and outputs, and not all parallel programs can be expressed in that way.
Thank you very much. I have marked it as answered. And let's go for the next one. There are many of them, so you tell us when to stop, okay? Next one. Do you think quantum classical hybrid programming would increment the security breach?
Oh,
yeah, that's the question.
that's an excellent question, and I don't have all the skills to answer that. We have people who work on quantum cryptography, post-quantum cryptography, because there's going to have many problems that are going to be solved, and among those problems, there's going to be some that are related to security.
Yeah, I understand that. And different scope. Okay. Next one. How do we balance the trade-offs between quantum acceleration and classical overhead in real-world hybrid systems?
That's also an excellent question, because like I mentioned, when we are scaling applications on CPUs and GPUs, okay, we have overhead because we need to send data on the GPU and we need to start something on the GPU. But that's a totally different story from the overhead that we have from running on a quantum computer. So for example, well, you've probably noticed that when you're starting a computation on a different node, on a different machine, on a quantum machine, there's some overhead that's absolutely not related to the size, the length of the circuit that you're starting. So it's really something that needs to be taken into account when you're designing your computation. So you're going to have for example, you're going to have your classical part, and you're going to have a classical part and a classical part, etc. And then you're going to have a quantum part here. And you need to take into account the fact that you're going to have, okay, the quantum part is probably going to be fast because you're going to use it on something that the quantum computer is super good at, but you're going to have latency. So you need to start the quantum computation on something that's really worth it and not just a couple of gates. You're really wanting to hammer this problem with your quantum computer, but at the same time, you need to take into account the fact that you're going to have some latency. So the classical part needs to be, well, it's also part of the scheduling problem that you have. The quantum part, the classical parts need to be long enough to overlap the classical part. And it's also part of, that's also part of the reason why I want to go from this model, where you have a classical part and a quantum part, etc. And I want to be able to, overlap that and to have something that runs at the same time there, and there, so that while you're running the quantum part, the classical computer is kept busy.
Thank you very much for that answer. I think it's very useful for everyone interested in this kind of hybrid systems. Next one. this had to be, does the ETS University admit Mexican students to pursue PhDs in Canada?
Well, of course, my opinion might be a bit biased because it's based on only a handful of students, but the Mexican students I've seen were really good, and they received a really good education in Mexico. So I would be super happy to have students from Mexico.
We hope many of our participants are interested, and we can make an
I
excellent
think there are
link.
some programs, some collaboration programs between Mexico and Canada.
Yep, yep. In fact, Dr. Boris knows about them, so
Okay.
maybe
But
later you can
I'm
send them
really,
an email. Yep.
We
I'm
have a
really open
student.
to.
We have former students doing PhD with Luke
Ah,
at
Melissa.
ETS.
Oh,
Yes,
yeah.
a former student of us is doing the PhD with Luke. Yeah.
So
Yeah,
that's
so I'm totally open to that.
fantastic. Next one, I think that will be almost the last one. Well, two questions more if you agree, Emil. Okay, there we go. I'm curious about examples of real-world problems that need distributed computing to be solved.
Distributed computing in general. So a very good, a frequent flyer for distributed computing is fluid dynamics. So for example, we have a guy in my university I collaborate with who is, oh, that's super cool. So he's simulating the flow, so fluid that's flowing. So basically the river. So we have one big river in Quebec, the St. Lawrence River, and he's simulating the flow so that he can compute erosion on the banks, and he can predict, for example, how bridges are going to be used and how the lifetime of that. Also, something that he's done is that he's designed so he's computing the fluid dynamics, but he can do that around arbitrary structures. So he's computing structures. So he's designing structures, and then he's computing for example, the speed of the water after that, so he can break wave, and he can reduce the energy of the waves before they're hitting the beach or the banks, etc. So that's something that's really, really popular. I have a student who's working on he's working on molecular biology. So he's basically computing properties on structures of RNA molecules. The thing that biologists are wondering is that can we find redundant structures in RNA? So in human RNA, but also in animal RNA, in the RNA of plants. So that can we find redundant patterns in RNA? So they have databases of RNA, and they're trying to we're trying to find redundant parts in these structures. So that's graph isomorphism, and the student is designing parallel distributed programs for that. The thing is that the people who tried that before my student were not doing it in a distributed way. So they were using a single machine. So they used a machine with 8 terabytes of memory, and that was not enough. So since we're putting together hundreds or thousands of machines, we can use all the memory, we can distribute the computation of the memory over that. There are also people who are using that to do you probably remember these persons who drew a black hole. So they captured data from telescopes all around the world, and they had to put together all this data to have the picture of the black hole, this big donut, and that was actually made possible by high performance computing, by distributed computing, because the data that they were handling was so massive that it couldn't be handled by a single computer.
Perfect. Those are great examples. And the last one, that it's going to become 2 questions more. Sorry. That's very tricky. Okay. Can we obtain a better visualization of qubits using another way or transmission mean?
Oh, that's an excellent question. So there are people researching that because, well, you've probably noticed that you can simulate the execution and you can visualize what's happening at the end. But when you're learning quantum computing, it's really hard to understand what's actually happening inside of your circuit. So I have a colleague at ETS who works on human-computer interaction who is actually focusing on that. So how can we visualize the state of the qubits and how they evolve throughout the execution of the circuit?
That's taken. Next one. Last one, I promise.
No problem.
Related to the question on applications, what about financial applications? Are there some uses of
Yeah, I know that
actually?
some people are interested in finance. So I don't personally know people who do that, but I know that it's a topic of interest for people from finance. So I work at an engineering school. There's a business school just next to us. So we don't have finance people in my university, so I don't know personally people who do that. But I know that, well, the thing is that quantum computation is really good at optimization and combinatorial optimization. And that's the kind of topic that finance people are interested in. So yeah, I know that there are some applications, but I don't personally know any of them.
Well, Camille, thank you. Thank you very much for all your answers. We have run out of time. And now I pass the floor to Dr. Boris to close this session.
Thank you very much. And thank you very much for all your interesting questions.
Thank you, Camille. Thank you very much for this very interesting talk. I have before closing the session, I have a question. I mean, when you have hybrid computing, with classical and quantum circuits and programs, I suppose that when you have programs in which you have to share data, you have you have to share data, and maybe they have to be shared between classical and quantum computing. How do you solve that problem?
That's a prime we have. It's part of the challenges that we're facing.
Okay.
I think you're going to have to so we're sending it over the network. So that's one particularity of our installation. We have the machines that are in the same room, so we have a networking between them. But then we have to translate them between classical and computing and quantum representation. So that's part of what needs to be taken into account in this DAG that I'm drawing.
Okay. Well, thank you. Thank you very, very much, Kamel. This has been a very enlightening, inspiring talk, and I think many people in this audience are triggered by this kind of research. I mean, it's a very interesting field of research combining high performance computing, parallel computing with quantum computing, and that's the real thing to get things done. No? That's the kind of thing that if you want to have a program that really uh, address real problems, these are the kind of problems you have to solve, to make this thing practical for practical problems. No? Yeah, so it is very interesting. I really thank you on behalf of the National University of Mexico. It's been a pleasure and an honor to have you in this session. I hope we can sometime meet again and overall collaborate sometime between ETS and our groups here. Thank you
Thank,
very
thank,
much.
thank you very much for your invitation. And I think it's the first time I was giving a presentation in front of that many people. So thank you very much for this opportunity.